Hello. In this video, I'm going to make a few comments in preparation for exam 2 and the final exam and try to kind of tie the course together. Visualization is a theme for this course. We tried to make an attempt at teaching it directly before exam 1, and we've been revisiting it here before exam 2, but it is needed at various points in the course directly as well. As an example, we have this diagram. We have right triangle RST, and we have an altitude drop to the hypotenuse, which forms two more right triangles. And this is the diagram that we use to prove the Pythagorean theorem. This is a wonderful diagram. It has three triangles that are right triangles, and these are similar. And visualization skills are needed to visualize the similar triangles. And we'll return to that later in the video. The second example I might give for visualization is visualizing the relationships in a pyramid. So let's jump over to the Wisconsin formula sheet that's going to be provided on exam 2 and the final exam. And we have down here an example of a pyramid. This happens to be a pentagonal pyramid with the apothem, the radius, and the three different heights. The slant height, which is MP, the edge height, which is CP, and just the plain old height of the pyramid, which is AP. And visualizing those right triangles is important, involving those heights, and the right triangle that's down here in the base. Triangle AMC is a right triangle as well. It doesn't really look like a right angle because of the two-dimensional representation of the three-dimensional object. We also have a physical pyramid here with the three heights. This pink one is the slant height. This yellow one is the edge height. And this one here with the blue tab is the height. And once again, it's important to be able to visualize all the right triangles. In this tetrahedron here, all four faces are right triangles. The next thing I'd like to do is to talk a little bit about proof and why writing proofs is a valuable thing, and also how we used proofs in this course. Here's a brief list of why it is useful for students to be exposed to proofs of theorems. First of all, it helps us understand the theorem itself by providing a specific but general instance of the theorem. Just looking at the given and prove sheds much light on the theorem. And for example, the triangle angle bisector theorem, just the statement of the theorem is maybe a little bit confusing. But when you look at the diagram and the given and prove of the proof, it helps you understand the statement. Secondly, by looking at a proof of a theorem, it helps us understand the theorem by realizing why it's true. Number 3, it helps us understand how to form a logical argument, which is sometimes rare in our society. Number 4, looking at proofs helps us understand the valid methods of proof. Now, most of the proofs we've done in this course are direct proofs, but there are other methods of proof, such as proof by math induction or an indirect proof. And finally, number 5, looking at a proof helps us understand how mathematics is built up. That is, math is built up from basic principles to construct more and more powerful notions. And mathematicians are still doing that to this day, taking known theorems and developing additional theorems. Now I'd kind of like to do a quick overview of how we used proofs in this course. First of all, we proved triangles congruent. And we looked at congruence here in weeks 6 and 7. And we started by just having a diagram and proving two triangles congruent, which is mainly just a useful exercise. But then the more useful thing was using congruence to prove properties. And in our case, we were proving the properties of the various quadrilaterals, parallelograms, trapezoids, and so on. Then in the second half of the course, we took a look at similarity. Once again, proving that two triangles is similar is fairly easy. In the case of similarity, you only need two angles congruent to two pairs of angles congruent, and that makes the triangle similar. Then once you have the triangle similar, you have all the proportions that you can write, and then those proportions can be used to prove things, including the Pythagorean theorem itself. As it turns out, using similar triangles and proportions, it could be argued that this is even more useful than congruent triangles in terms of solving problems, because there is a whole host of problems that can be solved using similar triangles and proportions. Another key idea in this course is transformations. There won't be too many transformations on exam 2, but they are fair game, of course, for the final exam. Reflections, translations, and rotations. And once again, it comes back to visualization. So let's go ahead and take a look at this figure here. And let's identify the similar triangles. This is good practice in general in similar triangles and good practice for the proof of the Pythagorean theorem. So we have the left-hand triangle, we have the right-hand triangle, and we have the big triangle. So let's take a look at the left-hand triangle and write that down. Maybe we'll call it triangle SVR. So let's get triangle SVR similar to the large triangle, and let's see if we can write the letters in the correct corresponding order. Corresponding to angle S in the left-hand triangle would be angle T in the large triangle. Angle V is the right angle, so that corresponds to angle S, which is the right angle of the big triangle. And then angle R is congruent to itself. Remember that these two triangles are similar because of angle. Angle R is congruent to itself, and they have a right angle. Now, one of the things that might be interesting to do here would be to think about transformations. Let's think about transforming this left-hand triangle into the right-hand triangle. Before we do that, though, let's go ahead and write down the similarity statement. The large triangle, triangle TSR, is similar to the right-hand triangle, and let's write those letters down in the correct order. Angle T will correspond to angle T. The middle letter is the right angle, that will be angle V, and angle S is the third letter. And then our conclusion by putting these together is that the left-hand triangle is similar to the right-hand triangle. We have triangle SVR similar to triangle TVS. And it might be interesting to be able to demonstrate this similarity using transformations, as we had on the homework prior to exam 1 and on exam 1 itself. Show a sequence of transformations that shows this similarity. Well, first of all, we could take triangle SVR and rotate it around point V 90 degrees to the right. That would bring point S prime down here. It would bring point R prime up here, and our triangle would be sitting here. That would be our first transformation as a rotation. The second transformation would be a dilation using a center point of V, and the scale factor would be VT over VS prime. And this will be a fraction larger than 1, which will make it larger. Another interesting question would be to show the similarity using a sequence of transformations to show this similarity. One of the challenges of this one is triangle SVR rotates around the triangle in a clockwise fashion, but triangle TSR rotates around the triangle in a counterclockwise direction, which means the orientation has been reversed, which means a reflection is going to be needed. So you might think about how you can transform the small left-hand triangle into the large triangle TSR. And it is going to require a reflection. You might pause the video to think about how you might want to do that. One way to do it is to realize that point R is already where it needs to be. So we don't really want R to move. So what we might do is reflect triangle SVR. Oops, let me get a proper pen here. We might reflect triangle SVR over the line that is perpendicular to RT through point R. And that gives us this green triangle. Then we would need to rotate this down around center point R, and then we would have to dilate to make the triangle larger so that it's going to fit and match up with triangle TSR. So the idea of transformations and visualization is used here with similar triangles. Another comment relative to transformations has to do with proving the properties of quadrilaterals. Back in week 8, I posted this handout, which is designed to help to visualize and remember how to prove the properties. So for example, if we are proving the property of a parallelogram, property 2a here, that opposite angles are congruent, we're going to draw in one diagonal and then prove the two triangles congruent. And then using corresponding parts of congruent triangles or congruent, we have the angles congruent. Then we need to do it again with the other diagonal. But the blue triangle here is similar to the gold triangle, and that can be shown by rotating the blue triangle 180 degrees around the center point. Let me go ahead and mark that center point. The red point is the center point, and if we rotate the blue triangle 180 degrees, it'll be right on top of the yellow one. Looking at the property of the rectangle, that the diagonals are congruent, now the blue triangle is congruent to the gold triangle. But in order to get the blue triangle to match up with the gold triangle, we're going to have to do a reflection. To return to this figure, I believe it's the case if we know any two distances, we can calculate all the distances. And I'm going to just make up some numbers here randomly. Let's say that ST is 8, and let's say that SV is 3, okay? Now, you want to be careful that you don't assume that this is a 30, 60, 90 triangle unless you have reason to believe that to be true. So you might think about what distance could be found first. I think I can find VT. VT squared plus 3 squared will equal 8 squared. 8 squared is 64. 64 minus 9 is 55. So I believe that VT is the square root of 55. Then I can use the left-hand small triangle and have it be similar to the right-hand medium-sized triangle and use proportions. So, and I can use that to find, for example, RS or RV. Let's maybe do it to find RS. So RS over 3, that's the hypotenuse over the long leg in the left-hand triangle, is equal to 8 over root 55, which is hypotenuse over long leg in the medium-sized triangle. So RS is equal to 24 over root 55. And we might simplify that, but I don't know that that's necessary. Now we could use the Pythagorean theorem to find RT, or we could use similar triangles again to find RV, or similar triangles to find RT. Maybe I'll do it that way. So looking at the right-hand triangle and the large triangle, let's see how we would set up our proportion. I want to find RT, which is my hypotenuse. And if I do 8 over RT, 8 over RT is in the large triangle. That's long leg over hypotenuse. In the right-hand triangle, long leg over hypotenuse would be root 55 over 8. And then if I cross multiply, I get 64 equals RT times root 55, and divide by root 55, and we get RT equals 64 over root 55. And then it's probably a good idea to check. Let's do the check here. On the left-hand triangle, 3 squared plus 64 over root 55. Wait a second, I think I've got a mistake here. Yes, I do have a mistake here. RV is not 64 over root 55. That would be longer than the hypotenuse. It's RT that's 64 over root 55. So let's calculate RV. Now, for the sake of time, I think we're going to run this into a calculator. We could get the exact form, but let's run this into a calculator. And we get 1.213558. Maybe we'll use 1.21356. And let me fix that on my diagram here. And now let's do a check. So our check will be 1.21356 squared plus 3 squared, and we're hoping that that's equal to 24 over root 55 squared. So I think I'll do the right-hand side first. I'm getting 10.47 on the right-hand side, and now let's do the left-hand side on a calculator. And on the left-hand side, I get 10.47 approximately as well, so I'm happy about that check. So in this particular figure, we have similar triangles and we have the Pythagorean theorem. So given any two lengths, you can find all the other lengths, and then once you have those lengths, you can find areas. It's a good exercise. And the last quick comment I wanted to make is the idea of doing things forward and backward. An example of this would be the 30, 60, 90 triangle and the 45, 45, 90 triangle. We have our relationships, and for example, if we have the hypotenuse in the 45, 45, 90 triangle, to get to a leg, we divide by root 2. On the other hand, if the leg is given and you want to get to the hypotenuse, you multiply by root 2. It's useful to be able to do these processes forward and backward. Okay, I think that's enough comments regarding the course. I really enjoyed teaching this course. Please give me a call if you have any questions or post them online in the discussion area. Have a great day.